Welcome back to the Deep Dive. Today we are taking on a problem that is, well, arguably one of the deepest challenges in the whole quest for generalized AI. We're talking about endowing deep learning models with human-level intuitive physics. We can get them to see things, we can get them to talk, but making them understand how a ball is supposed to fall or, how things collide, that's still this profound, really frustrating hurdle. So our mission today is a deep dive into this paper, Opinion. Learning intuitive physics may require more than visual data, by Su and others. And this is a great paper because it's so focused. It cuts right to the chase and asks, is this roadblock just about the scale of our data, or is the missing ingredient something totally different, like the distribution of that data?
Yeah, and it's such an important puzzle to solve because the gap in performance here is just enormous. The researchers really emphasize this. You have cognitive science showing that human infants, even kids under a year old, they implicitly get these core physics principles.
Like what? Object permanence.
Exactly. Object permanence, solidity, continuity. And they do this with almost zero explicit training and, a tiny amount of data compared to our models. And then you have our state-of-the-art video models, which have seen millions of hours of online video, and they're still performing just negligibly above chance on benchmarks like IntPhys2.
Right. That gap, that disparity between a human learning it with almost nothing and a machine failing with millions of hours of data.
Yeah.
That's really the whole thesis here. And the novelty of this paper, I think, is how they isolate that variable. They're not just throwing a new model at the problem. They specifically compared training on these huge generic internet video collections against a what they call the developmentally realistic visual data set.
That's the SAYCam data set.
Right, SAYCam. And they did all this using the same SOTA architecture, V-JEPA. Okay, so let's unpack that setup, starting with the goal. What exactly is an internal physics engine?
So the goal is to build that internal physics engine, which is a concept a few researchers like Battaglia have popularized. And the key here is it's not about running, slow, perfect simulations of fluid dynamics or something.
It's not a supercomputer.
No, not at all. It's about a coarse, probabilistic, kind of a gut feel mechanism that can quickly predict plausible outcomes in the real world. Think about what lets you catch a ball you've never seen before, or guess which way a stack of books is going to fall. That's the system we're talking about.
And if we want embodied AI that can actually function in the world,
it needs that. It needs that fast, intuitive grasp of dynamics.
Okay, so to see if that grasp can be learned just from video, they chose a pretty robust architecture. The Video Joint Embedding Predictive Architecture, or V-JEPA. This was a good choice, I think, because it's a self-supervised model.
Yeah.
Can you walk us through why V-JEPA was the right tool for this job?
Well, V-JEPA is fascinating because it isn't just passively observing. The whole point of the architecture is that it's forced to predict. It works by learning these latent representations in a highly non-generative way. Its main trick is it masks out huge chunks of future video frames and then has to predict the latent features of those masked areas, using only the frames that came before.
So by predicting the future, but in this abstract, latent space.
Exactly. It's inherently forced to learn the causal structure of the world, to understand, in its own internal representation where an object has to be in the next few frames. The hypothesis was that this kind of predictive causal learning process, it might just be flexible enough to internalize physical laws if you feed it the right data.
That does sound like the perfect architecture for world modeling. But then we get to the other half of the experiment, the critical part, the data. Instead of just scraping more YouTube, they used SAYCam. What makes this data set so special?
SAYCam is unique because it's supposed to directly mimic the input an actual child gets while learning. It's an egocentric video data set.
Meaning from the child's point of view.
Right, from the point of view of the subject. It's about 472 hours of video collected from 3 kids from age 6 months up to 32 months. And the whole rationale is that this kind of visual input is just fundamentally different from a clean third-person YouTube video.
Oh, so?
It's noisy, it's shaky. This is the crucial part. It is correlated with the child's own actions. The visual stream is filtered by what the child is curious about, what they're interacting with.
Ah, okay.
So the researchers thought that this developmentally realistic signal might contain richer statistical patterns, patterns that are necessary for grasping physical invariance, much more so than generic passive video.
But wait a second. 472 hours. Even if it's super high quality egocentric data, that's just a tiny fraction of what these massive internet scale models are trained on. Were they seriously thinking that 472 hours could compete with like 1.73 million hours just because the distribution was different?
Well, that was the core empirical question, right? That's what they wanted to find out. They needed to know if the bottleneck was truly data scale, or if just shifting to a developmentally appropriate signal could unlock better generalization, like it seems to for infants. If the SAYCam model did well, it would mean quality and distribution are king. If it failed,
Well, that points to needing something beyond vision entirely.
that sets up the experiment perfectly. So now let's talk about how they measured success. Measuring intuitive physics is tricky. You can't just ask the model what it thinks. So how did they adapt that classic cognitive science method, the violation of expectation paradigm, for a machine?
Right, so in cognitive science, you measure an infant's looking time. If a baby sees something impossible, like a ball passing through a solid wall, they get surprised and they stare at it for longer. The researchers basically translated this whole concept directly into a machine learning metric. They called it a surprise metric, and they applied it to a really tough benchmark, INFIS 2. This is a high bar.
What makes it so hard? It's built on photorealistic simulation. It gives you these pixel-to-pixel aligned video pairs. One is physically possible, the other is impossible. But it's designed to be tricky. It's got dynamic shadows, natural occlusions, and crucially, both fixed and moving egocentric camera shots, which really messes with model stability. And it's testing for those core concepts: solidity, immutability, permanence, and spatiotemporal continuity.
Okay, and for our audience who are deep in the weeds on this stuff, can we clarify how that surprise metric actually works mathematically?
Absolutely. The machine's version of surprise is just the difference in the model's prediction error when it sees a possible video versus an impossible one. For V-JEPA, this is calculated as the L$1 or norm difference between the model's predicted future in latent space and the true future in latent space.
So basically, how wrong was its prediction?
Exactly. It's just a measure of the magnitude of its prediction error. The model sees some context frames, makes a prediction about the future, and then we compare that to the ground truth. If the video violates physics, the prediction should be way off, which gives you a big older L1 difference, a high surprise score.
And accuracy is then just which video got the higher score.
It's even simpler. Accuracy is the fraction of pairs where the surprise score for the possible video is correctly lower than the score for the impossible one. It's a binary choice. Which video was less surprising to the model?
That is a really clean setup, a clear hypothesis, a tough benchmark, and this is where the results get, well, genuinely shocking. Because that whole hypothesis that a better data distribution could overcome a massive scale difference, it just hits an empirical brick wall. Let's look at the results. They tested 4 models. Let's start with their baby, the V-JEPA model, trained on the SAYCam data.
V-JEPA SAYCam. It got 0.50 accuracy.
50%. So a coin flip.
That's exactly chance. And that's our baseline. Now compare that to the giant model, the SOTA V-JEPA2HVM22M. That one was trained on, what was it? An astounding 1.73 million hours of video.
And its score.
A negligible 0.52 accuracy.
But wait, hold on. Are you telling me that a model trained on 472 hours of baby cam footage performed basically identically to a model trained on 1.73 million hours of internet video, a 2 percentage point difference?
That's precisely it. The critical takeaway here is that all the models they tested performed at or just barely above the chance baseline of 0.50. You know, they also had a model trained on an intermediate amount, 128 hours of general video, that got 0.54. Another architecture, MAE, on the same SAYCam data got 0.53. But the main finding is just crystal clear. Performance on these intuitive physics tasks, it does not scale with the sheer size of the visual training data.
That has to be the most damning result in the whole paper. It's implying that for this particular task, the difference between about 500 hours and nearly 2 million hours is functionally zero. The data volume just isn't giving it the signal it needs to generalize.
And it's not like it's failing on just one specific thing. Their detailed analysis in Figure 1 shows this failure is universal. The performance is consistently poor, always below 0.62. And that holds true across every single category they tested. It doesn't matter if it's solidity or permanence or continuity.
Easy, medium, or hard difficulty.
Same thing. And critically, it doesn't matter if the camera is fixed or moving. This isn't one specific weak spot. It is a systemic, fundamental inability to learn generalized physics from this data.
Wow, and that's just humbling when you put that 0.50 score up against the human baseline. What was that again?
From the original INFIS-2 paper, adult human participants scored a near-perfect 96.44% accuracy.
So the model is just guessing, while a human has this incredibly robust causal understanding. So if the average surprise metric is giving us chance-level accuracy, what did the qualitative analysis, the frame-by-frame surprise, show them about how these models are failing?
Oh, that's just as revealing. What they found was that the frame-by-frame surprise predictions were actually highly similar for both the possible and the impossible videos. What that means is the model isn't reliably registering that specific moment of physical violation. The instant the two objects pass through each other has a big spike in its prediction error.
It's not surprised at the right moment.
Exactly. The model is basically just as surprised by a ball rolling normally as it is by that same ball teleporting across the screen or flying through a solid wall. A human's high accuracy comes from a huge single spike of surprise right at the moment of violation. The models, on the other hand, are just generating noisy prediction values the entire time.
So they're just classifying based on the average of that noise.
Which is essentially random. The fact that you don't see that localized high magnitude spike just confirms there's no systematic internal physics model being formed.
Okay, so where does this leave us? What does this mean for the future of world models? The paper's core conclusion seems pretty unavoidable. Pre-training V-JEPA, which is a leading predictive architecture, on even a carefully curated, developmentally realistic dataset like SAYCam. It just wasn't enough. The challenge remains unsolved by just manipulating the volume or the distribution of visual data alone.
And this leads right into the limitations the authors themselves acknowledge and their proposed path forward. They point out two key limitations. First, SAYCam at 472 hours is still way smaller than the lifetime visual experience of a child. But the second limitation, that's the real philosophical takeaway.
Which is?
SAYCam only captures visual information. It completely lacks all the other critical aspects of embodiment.
Ah, that's the pivot. If vision isn't enough, what does embodiment add to the learning signal that's so important?
Embodiment introduces that closed sensor-motor loop. It's the constant reconciliation between an agent's own actions and the sensory feedback it gets, like haptic and proprioceptive feedback.
Right. Kids don't just watch videos.
No, they push things, they drop things, they crawl around, and they are constantly matching their intended motion with the actual visual and physical results. That active interaction, that provides a much, much stronger signal about causality and physical constraints than just passively watching something happen.
So the authors are proposing a move towards new kinds of data sets.
Exactly. They strongly propose that we need to be using embodied data sets. So yes, they should be egocentric, but also, crucially, they need to be multimodal and action annotated. They even mention a data set called BabyView, which integrates accelerometer data with the video.
So you get a direct physical signal.
You get a direct non-visual measure of motion and impact. It's a pure physical signal. And that might be what's essential for grounding a world model in actual reality.
And if you connect this back to the big picture, self-driving cars, robotics, generalized agents, the whole thing, this pursuit of intuitive physics, is directly tied to making effective, efficient, embodied AI. This study really seems to imply that trying to extract a physical model from purely visual self-supervision has hit a hard limit. We've kind of proven that a different data distribution isn't the magic bullet.
Absolutely. The performance floor we're seeing, that 0.50 to 0.54 range, it suggests that it doesn't matter how sophisticated your latent prediction architecture is. If your only input is passive vision, you are missing the fundamental signal. The representations you learn are great for, say, predicting pixels or video compression, but they don't seem to generalize to the abstract causal reasoning you need for even basic physics. The path forward has to involve integrating the agent's own physical interaction with the world right into the learning objective.
Which leaves us with a final, provocative thought for you to consider, and it builds directly on these findings. If self-supervised latent prediction using only vision is fundamentally failing to build a useful physics engine, does that mean the core cognitive mechanism of human intuitive physics relies on something inherently non-visual? Could it be that it's all about active closed-loop control, signals action, proprioception, haptic feedback, that the task isn't predicting what I see, but rather predicting what happens when I act, making the true learning signal one of action and consequence, not just visual sequence?